This kite surfer is not only having fun, he's illustrating the laws of physics. Let's draw a free body diagram of the forces acting on this surfer dude. The kite strings pull on him with a tension T directed upward and forward. The force of gravity pulls straight down on him, and the water exerts a force up and back through his board. Assuming that he's moving across the water at constant velocity, then the vector sum of these three forces should be zero, that is, they all cancel. This is a general condition for equilibrium, that the vector sum of the forces should be zero. With three forces, F1 plus F2 plus F3 should sum as vectors to zero. Another way to think about it is that the third force must be equal in magnitude but opposite in direction to the resultant of the first two forces. In this lab we produce the two forces F1 and F2 with hanging weights and measure F3 with a force sensor. Begin by making a graphical prediction. Take graph paper with a large square for each centimeter. Draw an arrow to represent 3 newtons in the horizontal direction by setting a scale of 4 centimeters of distance on the graph representing each newton of force. Draw a vertical force scaled correctly to represent 4 newtons of force. Use a ruler to measure the straight line distance from the starting point to the ending point, and then divide by the scale factor to convert back to newtons of force. According to the Pythagorean theorem, this should be a 3, 4, 5 right triangle with a hypotenuse of 5 newtons of force. Begin the actual experimental work by placing the sensor directly across from a hanging 1/2 kilogram mass. Since weight is mass times gravity, the weight is 1/2 kilograms times 9.8 meters per second squared, or 4.9 newtons. The white string is of a length to connect the force sensor, whereas yellow strings run over the pulleys to the hanging weights. Flip the range switch over to plus or minus 10 newtons maximum force. Make sure that the strings on pulleys are exactly horizontal above the force table. If the string is not horizontal, loosen the nut, adjust the pulley angle, and then retighten the nut. In Data Studio, indicate that a force sensor is in use. Set the sample rate to 1000 Hz. These force sensors must always be calibrated before first use in a given lab. We must ask it to sample 2 forces of known strength, and Data Studio can then interpolate all forces after that. Begin with no tension in the string. Type in 0.0 newtons for the amount of force, and then take a reading. Now hang 1/2 kilogram. Indicate in the appropriate box that 4.9 newtons of force are being exerted and take a second reading. Drag and drop the digits icon from the displays area onto the force sensor icon at the upper left. Magnitudes of forces will be displayed in the digits box in newtons. Since more precision is desired, adjust that option in the digits box. Our first 2 forces will be set up at right angles to each other. One will be directed along the x-axis, that is, the 0 angle on the force table. The second force will be pointed along the y-axis, or the 90-degree angle on the table. The resultant vector sum of these two, r, which exists only in our imagination, has a magnitude given by the Pythagorean theorem as the square root of f1 squared plus f2 squared, and will be directed along an angle theta given by the inverse tangent of f2 divided by f1. The third counterbalancing force required to keep the central point in equilibrium is provided by the string to the force sensor. In this bird's eye view, you see the force F1 with magnitude m1g pointing to the right along the x-axis, F2 with magnitude m2g pointing along the y-axis at 90 degrees, and the string tension from the force sensor balancing them both. Make sure that the intersection of the 3 strings is in the dead center of the force table. Read the angle of the force sensor string. Push the Start button to read the magnitude of the tension in the string connected to the force sensor. The force provided by the force sensor string, shown pointing to the lower left, should have a magnitude equal to your prediction for the resultant r using the Pythagorean theorem. Also, the force sensor string angle should be 180 degrees opposite the angle predicted from the resultant of F1 and F2. Let's now rearrange the two forces so that they are 120 degrees apart. The x-component of r is F1 plus F2 cosine 120 degrees, and the y-component is F2 sine 120. Use the Pythagorean theorem again to predict the magnitude of r, and the inverse tangent to predict the angle for r. Here is the force table view. And from above, you may now record the angle for the force sensor string, and push the start button to record its magnitude. Again, the magnitude of force from the force sensor should be equal to the theoretical prediction for the magnitude of the resultant r. The angle for the force sensor string should be 180 degrees greater than the predicted angle for the resultant. Rotate the force F2 over to a 60-degree angle. Here the x-component of r is F1 plus F2 cosine 60, and the y-component of r is F2 sine 60. This gives a prediction for the magnitude and direction of r. The setup is similar to what was done before. Record the new magnitude and direction for the force sensor string tension. Compare the magnitude and direction of the force sensor string tension with the predictions for r. Combining three forces into a resultant is not much more difficult. The x-component of r is found by adding the magnitudes of each force times the cosine of its particular angle, and the y-component of r is obtained by adding the magnitudes of each force times the sine of each angle. The third force may be added to the mix using the hooked string slipped through the center ring. Here are the various views of the situation. In this case too, the force on the force sensor should be equal and opposite the predicted resultant force of vectors F1, F2, and F3. This lab carries an important object lesson. When the forces in your life are not in balance, you will lose your equilibrium, and the sailing could get tough.